Okay. So I have studied music before my computer science studies, and I'm really interested in this topic of sonification in surgical application, in particular in minimal invasive surgery. Because I want to play some sounds for you in my presentation, I will play a sound, and I would be happy if you can give me feedback that you can hear this arpeggio sound. Okay, perfect. So during the past few years, we have collaborated with many scientists and researchers from different fields of studies, from art and human science to very high-level surgeons from different countries to fully understand the problem and the perceptual problem in medical field inside of the OR, and to be able to provide intuitive and user-friendly solutions for these problems. As an example to open up the discussion about why we need sonification and auditory feedback inside of the OR, I want to show you this video from ophthalmic surgery. On the left-hand side, you see the fundus image, which is the microscope view of the surgeon. And on the right-hand side, you see the intraoperative OCT, which visualizes microstructural anatomies of the eye in real time. In such cases, surgeons are usually interested in following the position and state of even to 5 points at the same time, which is even for most experienced surgeons very challenging and difficult. In most of the cases, surgeons ignore to use the OCT intraoperatively, which provides very valuable information in OR, but they prefer to focus on fundus image as they cannot manage to cover all the visual complexity at micron level. So one solution could be providing sonification and sonifying the information on OCT side, and let the surgeon be focused on fundus as they used to. And this multi-sensory feedback would be one of the solutions in these cases. And generally in minimally invasive surgery, as we may know, we all know that surgeons have very limited access to the patient body, and this will challenge them in different ways in hand-eye coordination, cognitive load, as we have many different visual displays inside of the OR, and the most dominant way of presenting a vast amount of data that we currently are able to process and analyze intraoperatively is the visual channel, which leads to visual overload for the surgeon. So our auditory system, as Matthias said, has great advantages, especially in terms of in temporal advantages against visual, in terms of capturing high complexity and multidimensional data. Our auditory system is capable of processing high temporal and spectral resolution data in very quick manner. So, but this, so we know that auditory feedback has advantage, but it has also challenges, especially in medical, that we have very complex data. We have a high dimensional and huge amount of data that we want to provide, that surgeons doesn't miss them intraoperatively. But at the same time, when we want to sonify all these information channels through sound, that would be also challenging in terms of usability and intuitiveness, and also the pleasantness of the sound. Imagine that we want to sonify all the layers or information that we have through acoustic feedback. And using conventional simplistic synthesis technique, we may end up with sounds like this. Okay, I hope that you are also agree with me that this design doesn't work inside of the OR, maybe also outside of the OR. But sonification as the systematic transformation of data into acoustic space provide us with different methodologies and paradigms to deal with these complexity and these design challenges. The very well-known example of sonification, as we may all know, is the parking assistance by cars that provides information of the distance to surrounding areas and obstacles. The first application that we focused on in medical to sonify the data for the surgeons, we targeted the task of ILM peeling in ophthalmic surgery, where the surgeon approximates the tool to retinal layers to peel a very thin membrane layer called ILM. And the challenge in this task is that the surgeon should operate on the retina or even subretinal area, which is very dangerous, extremely dangerous for the patient safety. So the idea was to provide the information about the area that the tool is located in a very pleasant and joyful manner. And this example that I show you is based on a musical sonification that we propose. Here in this work, we used granular synthesis as a method of generating sound, which operates based on the microsound timescale. And in this sense that we split a pre-recorded music track into small pieces called grain into 1 to 50 milliseconds. And then we modify the characteristics and features of these sound samples in real time. This is another example of the same method on surgical video. Okay, next work has focused on typical surgical tasks like closing the tool to a predefined target or perception of the force applied to a predefined surface or angular deviations. And this is one of the examples that we designed for this task. next example shows angular deviation from a predefined target using the same concept. Here we used physical modeling synthesis as a technique that we generate a model based on our data, and we create this model in a way to define, by defining some physical and mathematical equations to transform this model as a sound capable system so that the user can interact with this system like musical instruments, and the sound is generated based on data set that we created the model based on. These were pretty much older works that we have done. The last work I want to show you is about tool alignment, sonification to guide surgeons to a predefined target trajectory. One of the challenges in sonification and is the data complexity, and the idea here was to model the alignment task into a 4-degree of freedom task, and we were interested to know how we can present this complexity of 4-dimensional alignment through sound. So we divided the task into 2 subsequential phases. First, we fixed the entry point, and then the angular deviation. This is a very short example of the method and the experiment we have done at Balgris Hospital in Zurich. So we conducted a user study for pedicular screw placement tasks on phantoms with 17 surgeons, orthopedic surgeons, and our primary measurement was the accuracy of positioning and orientation alignment. Our results have demonstrated that sonification can be accurately used similar to visualization as we compared our system against standard visual navigation system. And we showed that our system can accurately support surgeons in terms of alignment. Now I want to just finish my talk and summarizing that sonification as an emerging field of research has been shown to be promising in medical field. However, we need to design more generalized systems to cover different kind of data and applications in OR, and also we need more studies regarding training and learnability and usability of these systems. Thank you very much, and I would be happy to answer your questions after the session.